everyone. As Carlos said, I'm not astrophysicist, so I'm basically a computational plasma physicist. So I did my master in something called master physics engineering. That is, we have kind of both 50-50. You have, it means that in final year you can decide which direction you have to go. So I chose to be a physicist, and I did my PhD in computational plasma physics at least. So why I'm here is just to show you some of ongoing effort that we are that is going on in Cineca. I'd say perspective and prospective. It means like there are some thoughts that I want to lay down, and I hope that it follows after this presentation as well, right? So I'm here together with my two colleagues. So I lead the astro and plasma physics related work together with my colleague Alessandro, Caterina, and also one of my colleagues who recently joined this group, Michael Renenti. So most of you know Alessandro and Caterina. We have a huge discussion this morning, so I think I don't need to go in detail. But one thing it should be very clear that all of us has kind of a background in astrophysics, cosmology, or plasma-related research, right? So the idea is that we understand what it is, but also we get to work with the computers and just that is what is one tools we have additionally, right? So this talk is not going to be specific to a particular research topic. So please, if you don't learn after this talk, don't mean this talk is never meant to be like this. So there is no learning, but what you will get the information from Cineca. Okay. So that will be my agenda. So I'll give you a perspective why we need to support astrophysics and plasma physics research at Cineca. What is our research going on? I mean, the research in some sense would be a bit naive for us to tell that we are driving the same level of effort as university does, but what we do basically we work along with. So that means we are not on the driving seat, you are still in driving seat, but we are there to help you, right? And I tell you what means by that. Then there's a current activity that we are following. That means is a project. I mean that's we are which is almost finished. It's 1 year left. That is Center of Excellence Space, COE. And then I'll give you some perspective where I think we need to compete or we need to start looking at in that direction as well, right? Sometimes fear also makes us smart. So this could be a fear that we don't want to lose what easy things are going on, especially in terms of research. Okay. So why you want to support Cineca? If you see that Astro Plasma physics rate almost third, but there are particle physics. If you combine them, we are really on the top, right? So if you talk about in total physics, I mean, we have a lot of user base, and these are the user effort of. So it's just like how many users are using our system. We have this this table. So that means there is a strong interest using HPC Center, right, as our large system that allow us to actually host the project if possible, right? You can always apply individual grants by other means, but also you can build your own project. So
what is others?
So others comes. So you see there are others could be. So AI machine learning, you see they are very, but like for example, the new research area of research, right? Other could be also web services, right? So that could be several things, right? But it means they don't have large participation in others. They are very small, so we just put everything in one. So this is just scientific domain that where two fields are interlinked. I mean, there are a lot of correlation, astrophysics and plasma physics. And if you see, like for example, galaxy magnetic field, or these are the simulation result that you actually run with that. So gas mass, but you also have a plasma physics side where they try to understand those phenomena where the interactions are done by plasma particles. What are plasma particles? Plasmas are full state of matter. That means it has specific characteristics that work on. That means particles will interact via electric and magnetic field, right? And where plasma physics will be very interesting because you have very powerful lasers. And for example, in astrophysics, one of the important question is when you have everything evolved from some initial conditions, some magnetic field that amplify. Where this magnetic field comes from, right? So you can have some light interacting with plasma, background plasma. You can see this Birman battery, this magnetic field can be generated, having those kind of magnetic field. Or in gamma ray burst, where you have electron and positrons, they are interacting with external medium. They would also generate some magnetic field. This is what one of the important things to this, that this magnetic field is generated and magnified due to some peak that you can get radiation, right? So these experiment actually is possible to be done. So this is where the plasma physics comes in. To be honest, I just kept putting this perspective to show that how close they are, but there are research of plasma which is completely independent of astrophysics as well. For example, if you take the LSE, which is 27 kilometer of the circumference where you drive the beam of to certain energy. However, you can there is a research going on where you want to shorten this length by driving with particle beams to some GeV. So, but these all the research is being going on, and they have all been using our clusters. Now, okay. So, what is our long-term goal? I mean, that is where we are. We really want to support Italian research, especially related to astro and plasma physics. But it's not that we are limited. We are very conservative. We are always open to even research centers. The main idea would be how we can ensure there will be no gap between SPC center, university, or industrial partner. I mean, a lot of the code development you see, there are new techniques that have been developed. For example, there is a workflow that some companies are working on. We can, or SPC center that you need to access large SPC systems, we could provide it. So the idea is really that we need to interact more from our side, but also I would like to university to be as active as we are, right? And of course, university will always have their simulation, their code, which need to be coded on GPUs, or it needs next generation numerical method. We can work together with. Again, we are not saying that we want to take your place. The idea is that you will be in the driving place. We are just a helper. So as a Cineca, we have infrastructure that we leverage to research institutes, not only Italian but also European. Most of the discussion had in the morning, so I'm not going to be very in depth, and I'm going to skip some of the part. Basically, what you have, you have two models. One is a booster side, and one is just purely CPU. Okay, so data partition and booster model, what we call model, which is node which is connected to GPU. Okay, so when you first time log in on the cluster, doesn't mean that you have a direct access to GPU directly, right? You log in on a node which has dual socket, almost 64 core per node, and there is no GPU. So how do you access that? That is the idea. So either you have interactive way, so you launch interactive task, and then you get one node which is attached to GPU, or you apply running by Slurm, right? You launch a job by giving a space flag in your dispatch file. So what GPU partition has, what you have, each node is attached to 4 GPU, right? So when you access resources, each node you have 4 NVIDIA GPU. It's not the most latest one, but it's Ampere A100 with the Intel CPU attached. So that means there is a fast interlink between CPU and GPU. This is where the things become very complicated when you work with application, because you're not in the homogeneous system. What it makes is heterogeneous. Now you have to play with 2 different systems. What this system offer is a peak performance of 309 petaflop. I mean 248, right?
It's 140
Two-
the actual one. This is the theoretical.
This is a theoretical one, but actually what you get
It's
200.
ranked in the top 500 with
Exactly.
240.
Exactly. So basically, what you get even 248 petaflop is a lot of compute power. Okay. Then you have this data centric part, which has a 1536 node, and the peak performance is 13 petaflop. I mean, there are a lot of discussion we did in the morning. That's why I'm trying to not going in detail, and also it's a bit redundant discussion. And this is how you see that they are connected. It's something called what's called dragonfly topology. That means you have 2 layers of factory. They are all interconnected. You can see the mass of these hard devices. They are connected, booster and data centric part. Okay. Katrina already talked about fast tire and capacity tire. This discussion this morning. So again, I'm skipping this part. One thing I want to refresh your mind is that how do you access this cluster? There is this is Italian. Let's say this is Cineca invented project. That means any Italian institute can apply. Iskra B. There's a class B, C, and D. Please read the specification. Iskra B is scientific based, so that means you have to present a scientific case. Iskra C is a small account, but it's more or less like a code development, and it's very easy to apply and easy to get. And Iskra D, as this morning, Katrina talked about the storage related account. Okay. Apart from that, you can also apply USB-C and extreme scale, regular scale, and you can see that benchmark and development scale is rather simpler. The idea is that you let people to try any USB-C cluster, not only Leonardo but also Lumi or Astro, but for code development they are very easy. But when you go regular and extreme case, where you have to present scientific case, things become very complicated, right? With lending, right? That's why where Scrubby is better. So you should take advantage of that. There is a special category which Katrina already talked about this, but she always send email, so you can get this. So that means there is a dedicated resources, Cineca resources to enough people. So please take advantage of this. That is the idea.
They're called Pleiade.
Sorry?
They're called Pleiade.
Yeah, the call is called Pleiade.
Yeah. Okay. So apart from resources, hardware, which you will never see, you will just access from terminal. What else we can do? That means we need to be in person, talking to each other. Time to time, we organize, every year we organize 2 weeks of summer school. Okay. Then we have also 1 week. Last year, Alessandro and Katrina took over. This last year, they organized 1 week of school just dedicated to physicists. That means we don't care. I mean, at least you should know one programming language, but we don't care whether you know what Slurm is or what is MPI is, what OpenMP is, or GPU programming is. We English. That's it. Yeah. Time to time, we have also organized hackathons, workshops. It is open to almost everyone, so please do participate some workshop or some invited talk. So if you're willing to show us that can also benefit to us, just reach out to us. We organize a date for you, and then you give talk. Like Antonio is going to give a talk on the 3rd of June. So that is one of the collaboration is the one thing that I really want to emphasize is there any room for us to work it together? That should be the main idea. Again, we are not stressed about grants. We are not stressed about writing paper, but working together is what we want. There is a website called eventichineca.et where you can find all the pre-recording code repository and slides. So you can just go and check. It's absolutely free. There is no, you don't have to even log in. There's a guest entrance. You can just take it. This is good, right? So you see that apart from hardware, we are also making effort where else we can. Then here it comes. What else? This is journal for everyone, but now is specific to Astro and Plasma Physics Group. If you are using one of these code, that means if you have any trouble compiling, running code, we are able to help you. Pluto is the MHT code, Open Gadget that Antonio also work on. IP3D is the plasma physics code, which is implicit. There is Osiris, which is I use the code. So all this code, there is Axiom space plasma, other space plasma code that solve a specific problem. All these codes are available. Is open source, so you can if you want to solve a physics problem, just get in touch with us. Have your problems, what you want to simulate, and also you need to have completion hours. So just apply SCSI, work with us. If you have any problem compiling or running simulation, we are there to help you, right? Apart from that, there is HPC tools that we can and we will provide. There is Michael, my colleague, he's working on this called automatic benchmarking. So normally what you do, you write a lot of batch file and then you always tweak it and very lengthy process. The idea is that you have Python-based reframe that does regression tests and everything automatic. And we are also creating kind of a dashboard. That means you run your simulation, your data is sent to somewhere else, you look at it on a web browser, you want to save the file to your PDF, like PNG file to your paper, you should be able to do it. So there is effort on going something that can use your time. You focus on more solving physics problem rather than evolving on this. You would use some tools when you have your own code that you want to profile it optimize it. So there is a tool called Scorpy that's we have actually experience on running this. Also, we have this application on Unardo. Especially when you're working on a GPU, you need NVIDIA profiler. Again, we have a lot of experience on using those profiler. That means we can help you, guide you where the bottlenecks is when you are putting your code. There is a visualization tool. It's not yet there, but one day we will have it. That means any astrophysical data you will give, and you will be able to have a very nice plot, as you saw one of my plot there. Spark Manager, all your compiler, all your application depends on some libraries. There's a lot of dependency. We can use Spark. Katrina and the group actually are very efficient installing lot of libraries for you, which is very easy to handle. Where me and Alessandro and Michael will have expertise of code development. We know what CUDA is. We also work with directive-based approach, and of course MPI, OpenMP, everybody knows. Michael is the one who is mainly handling for CI/CD part. That means everything is, it's, let's say, industry level, right? This is what industry follows. This is what our aim is. So from scientific code to managing your tools and visualizing all these things that we would like to have, okay, and would be open for everybody, okay. So of course there is no free food. You have to pay. Our salary should be paid by some project. This is where space project comes in. Another thing about having a project is that you are very directional, like what you want to achieve. Everything what you have written, you have to do it, right? So this gives extra motivation for us. So what space is a scalable parallel astrophysical code for exascale computing. We are moving towards exascale computing. That means we're able to do something 1 10 to the power 18, 10 to the power 18. That is it, right? So you'll be able to do all this stuff. Is
I take the question, yes.
no. Okay, so so the objective is that of the space is that you have open source code which has a very large user base, and you want to prepare this code to be able to run on large heterogeneous systems towards like Jupiter, that one is coming in Germany, would be able to leverage all the GPU resources, right? That is one idea. But one of the promise that we are giving in this case is that we just don't want to, of course, we will provide the code, open source, everybody can use, but we also train people if they need like running GPU or OpenGadget. There is a training, dedicated training, and there's workshop happening as well. That can actually let you get familiar with code, running the code, and doing your science. That is the idea. So we want to create skilled talent pool in Europe only for European. So now I'm stressed. So so you have 5 application, 9 universities, 6 HPC center, that is private company and HPC center. Where we are is basically work package 1 and 2, where we optimize and code the code. Okay. Yeah, so I'm gonna skip these. This is where we started, and that's where we are, right? So the space project is started in 2023, and now in 1 year we will finish. We have diversity of the code that we are working on. Is G-Pluto, OpenGadget, and IPIC3D. They are all different algorithms. They do different science. Okay. So there is a diversity of the code. And here is some benchmark. And of course, I can brag about this. They are all performing better. So let's keep this. Why you have to run port your code on GPU? Here is one example. This is work done by Vivreta. She ran the same test on CPU, which takes 9 days and 7 hours. When they uploaded the code and they run the same test, it lasts in 12 hours. Okay, so that is the advantage you have. Okay, yeah, gonna skip this. Okay, prospective. All this code you see, they are grid-based. That means they have some limitation. And limitation is that when you want to resolve a smaller and smaller point, means that computational costs become very, very expensive. This is where people are adopting machine learning techniques. In these things is quite known, but these techniques needs data, right? Your simulation data, they can train. One of the things that I was discussing with you. But that means you always need to rely on the data. That means you need to adopt new approach. That is where physics in quantum network is coming. Instead of you relying on the data, you can directly solve equations based on the Python-based machine learning model. So all the inputs you become your neural network, and you have a single output. You do the automatic differentiation, some loss function that you compute, and that is where at least NVIDIA, this is where it's driving, right? So NVIDIA has this modulus which solve partial differential equation directly and visualize it, right? So the idea is that can we be in the position where instead of you being very running a lot of simulation, but you run few simulation and you run these models because they are very computationally less expensive and be more closer to the real simulation. This is where trends are. Okay, I have no time for this, but that is the one thing that I did to understand how we can fit it. So you have a scientific problem that you want to solve. You have by means of two. Either you solve conventional math mass algorithm, right? That Jupyter and IPC they have. You write your own software, you always have to adopt new hardware, you make sure that they run, you post-process, and then you find out that your final result, which has to match theoretical work, right? Theoretical result. And this is what you always have to rely, but there are several processes. In case of PIN, you just directly solve a PED, and then you, by some benchmark, you want to verify if that is working. Especially if you look at CFD code, there have been many research going on in that area. Plasma physics side, people start to look at it, but other fields are catching up. This is where me personally, I would like to push that direction. So we have expertise on that, and very soon we will have a AI. Cineca is AI factory of Europe. That means you will have a processor that dedicated to machine learning, those kind of algorithm. So that means we physicists should be adopt new techniques and then make sure that we are not lagging behind and we follow the same trend. Okay. Yeah, I just want to show you the last work that when I say about PIN, what I did. So this was my work that been published in PID. I wanted to understand if I can train this model and can I have the same path, more or less same characteristics. So I just solve all these equations, and you can see the instability grows and you saturate, then it grows again. It basically follows this path. If I train more long enough, it means that it will accurately get what the result I have. But this is very naive because to run this simulation, I had to make sure that it follows current condition, it doesn't have numerical noise and all this stuff. Training this kind of model is a bit hard as well because either you're overfitting, right, in better. So it means you need to have a clear understanding of your physics problem. So once you know what the problem, what you expected, it's easy to work this kind of algorithm. Okay, summary. I have 1 minute. Okay. Yes. Okay. So conclusion is that please use us. This is short. You are expert of your field. Bring your project, your applications, and get to work with us. Of course, our knowledge may be focused to provide services or coding code, which is the demand. But if you want to work with us on let's say most let's say what is being sold, machine learning and a hybrid approach like PIN, what NVIDIA other companies are pushing, please involve us. This way we also be benefited and you also be benefited. That's all I want to say.
So let's start taking some questions from online. So I will read it, or maybe if you want to ask, it's okay. Okay. I'm gonna read it. Okay. Is Spark the new default for deploying software at Cineca? Is the Ancient module environment still supported or is deprecated now?
So we install everything by one. Huh?
If you want, I can answer.
Please.
Please
Okay.
talk here because otherwise
Hi, my name is Caterina. I'm from the production team, so I will answer that. Spark is the package manager that we chose, so it's a default now on Cineca machine. It's not the only one. It's very used for HPC systems, but like also, for example, EasyBuild. But we historically chose Spark. So the new modules, the new software libraries, tools, and so on are mainly installed with the Spark. Not actually everything, but mainly installed with the Spark. So the modules are made with the Spark, but you find the same module environment as always. So we still have the module environment, all the applications, the profiles divided by scientific fields. Just these modules are installed with the Spark. The compilers are installed with the Spark and so on.
And in addition, EasyBuild is the one. So there's kind of always debate whether you use Italian infrastructure, European infrastructure, or American. So Spark is basically, if you see like AWS, is manage everything by Spark. Spark is very easy. It's just choice, right? I mean, what you find easy to work with. I think that's why we chose Spark.
Okay, there is a question again online. Please, Marco.
Hello. Sorry for not being able to be there. I wanted to ask a question about a different code, not a code that you mentioned among the ones that you are supporting. But as you probably know, there is another version of Gadget, which is Gadget 4,
Yes.
which is widely used for large cosmological simulations and was made in order to be scalable on a large number of nodes and on cores. However, this code is built using a hybrid shared plus distributed memory parallel programming scheme. And unfortunately, most of this relies on the possibility of the code to access basically all the memory of the node as a shared memory. And this is typically not the standard default in the installation properties of large supercomputing center nodes. So the question is whether there is any possibility to request some adaptation or some modification of the installation properties of the memory on the nodes in order to make such codes working more efficiently. I'm talking specifically about the portion of shared memory which can be of the shared memory of the node which can be accessed, because typically that is set to 50% of the total memory of the node, but this is a strong limitation for a code like Gadget 4. And I asked already multiple times to the user support of Cineca, and well, in the end, I never got a positive answer. So it looks like that there is no, I mean, there is some fear in changing this setup, even though this is a strong limitation for codes like Gadget 4. So I just wanted to know whether there is a possibility to discuss about this.
Caterina?
Well, from a memory point of view, do you run on GPUs, right? On the booster?
No. Gadget 4 has no GPU.
Okay. So because on the data-centric and general purpose nodes, actually there is a quite huge memory that can be used, and that you can access with the variable TMP-dir. Are you aware of this? Because the compute nodes of the booster partition are diskless, so the only part of disk is it's on the RAM, and so you do not have so much. But on the data-centric nodes, there is a quite large disk. It's okay. I'm not remembering now. And so we defined a variable TMP-dir which addresses the path /TMP. And you can use it up to, can you check in the first slide? And so actually you can use a large memory if this is what you mean.
No, my question was about the shared memory part. So there is on every node there is a path which is associated with the shared memory. It's called SHMEM. And that is typically set to half the memory of the node.
Yeah, I think
I don't want to get into too technical questions for the.
I think this is most the choice of the system administrator, and we cannot change it. But you said you already asked, right?
Yes, so there was some attempt to try this, but then it never went to. I mean,
there are hardware limitations.
Yeah, I'm afraid it has already been discussed with the system administrator, and this is what we can do.
Okay, because this is a very strong limitation for a code like Gadget 4. So basically, it makes it almost useless, because it means that it has to be run on twice the nodes that it would be.
Yeah, I understand. But I will discuss it even more when I go back to the office, because
so maybe if we can get in touch with you and maybe have a more open discussion on this, that would be very useful.
Of course.
Okay, thank you very much.
Let's see if there is something else. Okay, so I see two questions. Do you also support running codes via containers such as Singularity or similar? And I take both so that we have everything together. Is there any plan to introduce the use of Docker, Singularity, or other container? Oh, sorry, same place.
Yeah. So I know that one of my colleague Massimo, he did this kind of effort on Singularity. You have to build everything on your local system. Then you have to this Docker image to Singularity, and then you are able to run. However, what I saw, the result is the test, benchmark test he did. This is another project he did for DE360. The scaling test, I mean, there's a lot of issue with this. So to be honest with you, we don't encourage right now to use, I mean, of course you can use it. That is the first answer. Second thing is that you don't want to do this because there's a lot of problems. And I think this will be very, very hard to maintain your test case as well. So yes, but it has some extra work.
Okay, so I think if everyone, do you have any other question? Otherwise, we can thank the speaker again.
So I could have a last question.
Yes.